Hello, everyone. So, to not to reward those of you who have come early, let's get started. So, are we recording, Bernard? Yeah. So, thank you all for coming. This is the last seminar slash research spotlight of the 23 year. And we are, I think, ending the best way possible with our first double author seminar. We are very pleased to have here Daniel and Andrea, who are the main authors of the AlphaDev algorithm that was recently published on Nature. And yeah, I think that it's best to give the stage to you guys. And thank you very much for coming.
Great. Yeah. Hi, everyone. Thank you. Cool. Yeah. Thanks for having us. Yeah, let's take you through this. So the general idea is that we're going to start by sort of motivating sort of how we started, how we came up with this, why we came up with this, why we wanted to optimize code. Then we'll take you through the Markov decision process, which we call the assembly game. We'll talk about some key aspects of AlphaDev, and then we'll take you through the sorting analysis and results that we got. And then we'll follow this by talking about the hashing, motivating the problem, analyzing the algorithm it discovered, and then go through some related work, some limitations, and then end. So Moore's law is coming to an end, and chips are starting to reach their fundamental physical limits. And as such, we need to find new and innovative ways in order to optimize the computing stack. So one way to optimize the computing stack is to optimize the software or code that runs on it. And we believe that there are many optimizations that are both non-trivial and or unintuitive that can potentially be discovered with the power of AI. So when we started this project, we sort of got together and said, well, what if we could automatically optimize the world's code using reinforcement learning? Potentially discovering entirely new algorithms along the way that can both influence how researchers and practitioners think about and implement their algorithms. But where do we start? So we decided to start by optimizing at the low level CPU instruction, at the CPU instruction level, i.e. the assembly level. So if you look at the figure on the left, this is a function written in C++, which is called variable sort2. This sorts up to 2 elements. And this is then typically compiled into assembly. Assembly is executed, you can see the equivalent program on the right in assembly. Assembly is typically executed line by line, and it involves manipulating values between memory and registers in order to yield the same outcome as the C++ program. And an example of an assembly instruction here is this move instruction, which is moving a value from register EAX to register EDX. And the reason we decided to start at the assembly level is because assembly gives us a lot more flexibility, and we thought that there would be a lot more hidden optimizations that we could discover if we optimized at this level, and hopefully that could translate back to the C++ function. And so the question was, where do we start? We wanted to start with something big. We wanted to start with something fundamental. And so we decided to start by exploring sorting algorithms. Now, sorting algorithms date back all the way to the great library of Alexandria, where Zenodotus was sorting the various books in the library. And then this extended to like in the 1890s when there were tabulated machines for counting votes. And in modern day, sorting is as simple as sorting 5 numbers. Anywhere you want to sort 5 numbers, for example, you will call the sorting algorithm. It's in applications from information retrieval, job scheduling, information display, recommendation systems, and string processing. It's really everywhere. And this was really a fundamental algorithmic challenge in computer science. So researchers and practitioners have worked on improving these algorithms and discovering new ones for decades. And we estimate conservatively that these algorithms are used trillions of times on any given day. And a lot of these, or most of the time, these algorithms are called from very popular libraries, such as libc++. And by improving upon these algorithms, we would hopefully then impact millions of programmers and applications and hopefully billions of users around the world. So how do we learn? How do we play this game? So the game, the assembly game, or the Markov decision process here, consists of a state space, where the state space is the algorithm that's been generated thus far. So basically the algorithm that it's building, because it does everything from scratch. In addition to this, we track the state of CPUs, memory, and registers. And this allows us, the agent, AlphaDev, as it's building the program or the algorithm, to be able to understand how this affects the dynamics of all the values moving through memory and registers on the CPU. The action space is the set of valid assembly instructions, and the reward is a combination of correctness and latency or speed. So the way this game works is AlphaDev receives as input the state. It then chooses an action, which in this case is an assembly instruction, that it then is going to add to the algorithm as it's building it iteratively step by step. Here it's chosen to add the move instruction from the value in register 0 to memory location 1. It then adds this to the algorithm, and then we need to reward the agent. So how do we do this? So if we think about sorting, what we do is we take the algorithm that it's generated so far. We then feed a set of input test sequences into the algorithm, and this generates a set of outputs. So in the case of sorting, we can then compare this to the expected outputs, which is that the values should be sorted. And then we reward the agent for how well it's sorting these outputs and penalize it if it's making mistakes. We do this until the agent discovers a correct program, and then we add the ability for the agent to optimize for latency. Now, when we optimize for latency, there's different ways you can do this. So one thing you can do is you can do proxies for latency. So you could optimize for things such as program length. But program length is a good proxy when latency and length are correlated. And this is something that you'll get in algorithms where there's no branching. So there's no if-else statements. You tend to get these correlations. But as soon as you have branching, which is in most of the algorithms that you develop, you then tend to get this to break down. These correlations break down, and it becomes critical to optimize for actual measured latency. But this is really challenging. And I think one of the most important aspects of our work was figuring out how on earth do we measure latency. Latency is very difficult to measure, because imagine you want to measure the latency of an algorithm, and you then run it, and it's measuring the latency on a process, and another process comes and interferes with that. And you have no way of knowing that the process interfered with that, and suddenly you see sort of a spike in latency, and you don't know whether it's just a poor algorithm or whether it's actually measuring whether there's something that added noise into the system. So we needed to develop a noise-free service that allowed us to accurately measure the latency of these algorithms, so we could use it as a reward in order to optimize for it. So what we did is we created what we call the latency benchmarking server. And the idea is that we created a set of separate machines that were separate from the training procedure. And the idea is that AlphaDev would then process 1,000 measurements across all of these machines. And for each measurement, it would process 10,000 random inputs. And we would take all of those measured latencies, average them together, and take the top 5th percentile of those measurements. And this, we found, made incredibly accurate latency measurements for our algorithms. We used the CPU performance counter called CPU clock unhalted core. And this actually enabled us to measure changes in latency on the order of nanoseconds. And this was incredibly important because a lot of the functions that we're going to talk to, or the algorithms that we're going to talk about today, that we optimized were quite short. And so you really needed to be able to have accuracy on this order of magnitude. So how hard is the assembly game? So because AlphaDev is building these algorithms line by line from scratch, it needs to be able to consider the combinatorial space of assembly instructions when building these algorithms. So the number of possible algorithms it can build is similar in size to the number of atoms in the universe, the number of possible games in chess, and the number of possible games in Go. And what makes this even more difficult is that a single incorrect instruction can invalidate the entire algorithm. So how do we efficiently explore this space? How do we essentially extend some of the core RL technologies at DeepMind, like AlphaZero, that has this ability to do search, to be able to efficiently explore the space of algorithms? And we found that there were two key aspects that we wanted to talk about. So The first is that the algorithm should have the ability to really understand the structure of an assembly program. It should be able to really understand the effects of adding an instruction to the program and how that affects the overall structure of the program. In addition to that, we need to have a way, we can't just measure latency at every step. We need to have a way to be able to predict latency accurately. And so these are two of the key components that we had. We developed what we called the assembly transformer. And this is something that you can see at a high level in figure A, where the idea is that we feed an the assembly program that's been generated thus far into the transformer, or the transformer encoder as we call it. And in parallel, we feed in the states of memory and registers through what we call the CPU state encoder. These are then combined together in a nonlinear way. And this is really important because we want to be able to associate the structure of the assembly program that we're building with the dynamics of how the states of memory and registers change. So these were two quite crucial aspects that we needed to combine together. In terms of the latency, we added what we called a latency value function. So a value function that was capable of predicting the long-term latency of a program, even for a partial program. And the reason we did this, as I mentioned, is that evaluating a program's latency is really expensive. And we can't do this, for example, when we're doing Monte Carlo tree search, we can't evaluate this at every single node, for example. And so the idea is that we ran a number of actors in parallel. And these actors were copies of AlphaDev that were effectively generating these assembly algorithms. And that was their job. As their parameters were getting updated, they kept generating assembly algorithms. And the idea was for these actors, each time they generated an assembly algorithm, we would then measure the actual computed latency using our latency benchmarking server. But what this allowed us to do is the actors form a very small part of the programs that are generated by AlphaDev, because AlphaDev is also generating millions of programs through Monte Carlo tree search. And so we only actually had to evaluate actual measured latency on 0.02% of the generated programs, which made everything much more efficient. We would then take these measured latency values and we would use them to train a latency value function head. So we would have a value function head that would predict correctness and a value function head which would be used to predict latency. And then during Monte Carlo tree search at each node, we would then use this predicted latency in order to update the agent or do the bootstrapping instead of actually measuring latency. And this really allowed us to scale. So the question became, well, we want to optimize sorting functions or sorting algorithms, but which ones? And we really thought about this a lot. And when we looked at the standard C++ sorting library, we saw that when you call sort n, so if you're sorting 1,000 elements, for example, this is going to call algorithms such as merge sort that are going to recursively break down the function and then call smaller functions of sorting ultimately 3, 4, and 5 elements, which we call sort 3, sort 4, and sort 5. And we realized that if we're able to find a way to somehow improve the speed of these fundamental algorithms, sort 3, sort 4, and sort 5, we then would hopefully be able to propagate this effect through to sort n effectively and speed up any sorting algorithm that calls these functions recursively. We also wanted to look at the capabilities of AlphaDev by looking at what we call variable sorting functions. And these are sorting functions where, for example, variable sort 5 can sort up to 5 elements. And here we introduce the notion of branching, where you need to be able to really, AlphaDev, because it's building these algorithms from scratch, needs to understand when it needs to add a branching component into the function. So it needs to build the main body and then understand when to build a branch in assembly into the main body that gets called by the main body. It basically makes it a much more complicated problem. And here again, as I mentioned earlier, the latency, the program length correlation breaks down. So it was really critical that we optimized for actual latency there. So the theoretical state of the art for the fixed sort algorithms, like sort 3, sort 4, and sort 5, are what's called sorting networks. And sorting networks are really efficient in that they generate conditional, efficient, branchless assembly code. And I'll just give you a quick overview of what a sorting network is, although you may have all learned about it already in like data structures and things like that. So in figure A, if you look at the horizontal lines, these are what we refer to as wires. And the vertical lines are what we call comparators. And the idea is that in figure B, if you take, for example, a set of unsorted values, 2, 3, 1, and 4, and you feed them through each wire in a sorting network, what happens is that when two values reach a comparator, they're compared, and the value that is smaller goes up, and the value that is larger goes down. And so you're essentially getting these numbers to flow through a sorting network to the point where they're all sorted at the end. So we thought, you know what, let's try and optimize sort 3. And we looked at it. It was 18 instructions long in assembly. We honestly thought that there was no optimization that could make it better. And we thought, you know what, let's just run AlphaDev and try and see if we can rediscover this baseline and then use this in order to try and scale this up and do larger sorting functions. And then to our surprise, it discovered a 17 instruction sort 3 program. And we initially thought that this was a bug, as you know, it typically tends to be. And we looked through this and we realized that it actually had found something that was one instruction shorter. And so we started to then try and analyze what this result actually was and why it was shorter. And so when we look at the actual assembly that it generated, on the right-hand side here is the assembly that AlphaDev generated from scratch to build this sort 3 program. And on the left-hand side is the original sort 3 function. And effectively what happened is it found a way to reshuffle parts of the program and remove this instruction 15 here, which is a move between two different registers. And so we wanted to sort of try and understand this further. Like, is this sort of a one-off thing, or did it learn something more general? And we realized it learned something that was a little bit more general, which we call the AlphaDev swap move. Now, if you look, in order to understand the swap move, if you look at the figure on the left, for 3 wires, we have A, B, and C as each of the wires. And the AlphaDev swap moves assumes that the values on wires B and C have already been sorted. And if they've already been sorted and you have the structure that's circled in red, then you can apply this AlphaDev swap move and save an instruction. So if we take an example here on the right, we've got 3 unsorted values, 2, 3, and 1. And you can see that 3 and 1 have been passed through that comparator, and now those have been sorted. So the assumption is in place. What we can then do is basically take 2, 3, and 1 as being the values on wires A, B, and C. Maybe I can point here, over here. 2, 1, and 3 on wires A, B, and C. This is for the original and this is for AlphaDev. And we can continue the program saving this instruction, which is this move SP over here. And the idea is that this was in this paper, and this I think caused also a little bit of confusion initially, is that this snippet of code that we showed is essentially the remaining part of the program after you've already got this assumption in place that B is less than or equal to C. And so this isn't a full sorted program, this is the remainder of the program, assuming that assumption's in place. And if that assumption's in place, and then you execute the program, you're able to save an instruction. So we said, let's go to sort 4 and sort 5 and see what we can discover. And for sort 4, we managed to discover from scratch the theoretical state of the art. So we matched it, 28 instructions. And for sort 5, we managed to find a 42 instruction program. So 4 instructions shorter than the state of the art. We also found a sort 5 program that was 43 instructions long. But what was very interesting about this is that when AlphaDev built this from scratch, it learned to apply the swap move 3 different times. Each time applying it in these red circles over here, and each time saving an assembly instruction. And it was actually this 43 instruction program that we chose to use to reverse engineer in order to submit to the C++ library, which I'll talk about shortly. We also discovered a move called the AlphaDev copy move. This appeared in a structure of a sort 8 sorting network. And it's a very similar concept to what I explained earlier, is that if you have the structure in the network where wire D is greater than or equal to the min between wire A and wire C, followed by this structure circled in red, you can then apply the copy move, and this snippet here is showing the rest of the function after this assumption is in place, allowing you to save an instruction, in this case the move PT instruction in red. So we were really discovering these sequences of instructions, which we called moves, that could really be applied when certain types of structures were observed. And this is something that we found quite exciting. So then we said, let's take this a step further. Let's submit these small sort algorithms, sort 3, sort 4, and sort 5, to the LLVM standard C++ sorting library. And we expected, to get feedback of like, okay, thanks, it's really cool, nice, try again because, this has been done or that's been done. And we realized when we submitted this that there actually was a chance that we might be able to get these algorithms accepted. And after a 3-month-long process of writing countless unit tests and going back and forth and really, praying at times, we actually got them officially integrated into the LLVM C++ library, sorting library. It was the first change to these subroutines in over a decade. And the improvements to the algorithms that were replaced in this library ranged from up to 70% for sort 5 to approximately 2% for sorting more than 250,000 elements. And what was really cool about that is that with our initial hypothesis that if we can improve these fundamental small sort functions, we can hopefully then improve sort n. And this is something that we observed here. And it was also the first time that automated code developed by RL has been added to a C++ standard sorting library. And so we also wanted to try and estimate how often we think these functions are called. And we think that our routines, we estimate they're now being called or used trillions of times every day. And some of the users you can find on the LLVM website, which includes many different large international companies. So we then said, let's go and look at variable sort. So now things become even more complicated. Now we need to understand the concept of branching. The agent needs, as it's building the function, the algorithm from scratch, to understand when to add subroutines, etc. And what we found is we initially said, let's optimize directly for length. And while this wasn't necessarily correlated with latency, we found that AlphaDev was capable, for example, in variable sort 4, of reducing the size of the program by up to 29 instructions. And this really gave us some evidence that, as functions become more complicated and bigger, there is potentially a lot of room or headroom in order to improve some of these algorithms or come up with completely different ways of building these algorithms. So we then said, let's optimize for latency. And we found that, again, when we optimized for latency using our latency benchmarking server, we were able to get significant gains on sorting up to 3, up to 4, and up to 5 elements, respectively. And I just wanted to kind of give you sort of an idea of like some of these algorithms that AlphaDev constructed. So on the right here is this variable sort 4 algorithm. This is the fastest one that AlphaDev found, which was 57 instructions long. And if you look carefully, it might be a bit hard to see, but you can see that it understands when to add jump instructions, which means to jump to a particular subroutine in the program. And this one here, for example, is one of these subroutines. So it understood how to basically build a function, the main body of it, understand when to jump to a particular subroutine, and then understand later on when to build that subroutine. So there really was a lot of complexities required by AlphaDev to understand and structures to capture in order to actually build this. And the types of algorithms that it built were quite interesting. So on the left is a human benchmark of variable sort 4, where the idea is you input a sequence of 4 numbers. If you input a sequence of 4 numbers, then you call sort 4. If it's 3 numbers, you call sort 3. If it's 2, you call sort 2. But what AlphaDev built was something quite different. The idea is that you would feed in your input sequence, and then it would compare the length and say, if it's 2 numbers, call sort 2. But if it's not, immediately call sort 3. And if it's 3 numbers, then end. But if it's not, and it's larger than 3 numbers, then it called a much more simplified subroutine to just sort the last two remaining elements because the first or three of the elements had already been sorted. And so it was able to save a massive chunk of assembly code, and this could then therefore be implemented more efficiently by having a different perspective on how you build these algorithms. So now I'm going to pass over to Andrea for the remainder of the talk. And yeah, I guess, and we can do questions at the end of the talk. Should that, yeah, okay. Great. Yeah, let's.
Cool. Thank you, Dan. So we went through the assembly game, we went through AlphaDev, how it works, and some of the analysis and sorting. So now I'll walk you through some of the comparison with other state-of-the-art approaches. And then we'll look at the question, can AlphaDev generalize to domains other than sorting? Spoiler is yes. And finally, we look at some of the limitations of the work, where does it work, where it doesn't, and where can we go from there. Cool, so for a baseline, we looked at the state-of-the-art approach, which is stochastic search, and we implemented a version of Stoch in the same setup that we have, and we call it AlphaDev S. Here we use the same assembly game that Dan talked about, and we same the same correctness routines when we measure for correctness, and we give a like for like in terms of resources and what clock time. One main difference that it's important to highlight is the latency value function, which Dan talked about. The latency value function is really the trick that allows us to compute latency end-to-end in an efficient way, because we don't need to calculate the latency for every program. Now, AlphaDev S doesn't make use of this latency value function, and that is a problem. Why is that? It's because for us it's now prohibitively expensive to compute the latency for every program that AlphaDev S computes. So what's the mitigation that we've done here? We optimize for program length. That means we optimize for shorter programs. And then out of all the programs that they have, like thousands, we compute the latency for all these programs, and we pick the best. And that's how we are doing the comparisons. So how do the two compare? Well, the first conclusion that we do is AlphaDev does outperform AlphaDev S when learning from scratch without prior knowledge. And what do we mean by prior knowledge? We mean starting from zero. So empty buffer where both algorithms come up with an instruction at a time. That is the setting where AlphaDev does very well, and the setting where AlphaDev S doesn't do so well. However, there is a second setting, which is the setting where we give a demonstration to the agent. And this is actually common. For instance, what we did is we take what's the human baseline, what's the best known sorting program there, and we ask the agent, can you optimize from there? And in this setting, AlphaDev S, we call it warm started, does quite well. It's very computationally efficient, and it does possibly better than AlphaDev in terms of resources and time. Then when we actually look at this, an interesting observation that we did is looking at how many programs they explore. And what we notice is that when the algorithm size increases, AlphaDev explores significantly fewer algorithms than AlphaDev S. Especially if you look at you can look at var-sort tree, AlphaDev S explores about 31 trillion programs, while AlphaDev only about 12 million. So massively different. So we had the one hypothesis, which is AlphaDev explores the state of programs better. And we tried to visualize this hypothesis, and we came up with this t-SNE visualization. What you're seeing in this graph is every dot is a different algorithm, and we compare AlphaDev, AlphaDev S warm started, and cold started. Cold started is starting from an empty buffer. When we look at AlphaDev S, it's very interesting to see how all the algorithms are very uniform, right, in the same bubble. It almost looks like it does a breadth-first search, right? It searches very locally in the space. Well, when we look at AlphaDev, the default setting, we see that the way it searches through program is quite different, right? It's not uniform anymore. Now, if we do the breakdown by correctness, AlphaDev S cold started is not able to find correct programs here. It remains in this area where all programs are incorrect. While AlphaDev, the default setting that starts as well from an empty buffer, it starts, of course, from an incorrect program because an empty buffer is not correct, but slowly finds their way through a correct program and then moves again, finding a correct and fast program. So that's an interesting way to analyze how these algorithms operate in the algorithm space. Cool. So we did a comparison with a baseline. Yes?
Is this t-SNE over the program embeddings from the transformer?
No, I think we include yes and no there, but yeah, go ahead.
So the t-SNE was what we did is we took for a whole bunch of programs. This was for variable sort 5. We took distributions over the instructions that were called in the program. So we had things like instruction counts, we had the latency. So we took a whole bunch of these types of features, and then we did a TSNE projection with those features.
And the other thing is the transform is a part of AlphaDev, but not the stochastic search. And then, cool, so this is comparing to Alpha, yes? So correctness in this case is measured for sorting. So we have an input distribution, we run the algorithms, and then we measure out of these inputs, how many of them are sorted. So this case is specific to sorting. So, and it's exhaustive search. So we exhaust all possible permutations, which is actually called the Bell order. So if you have a size 3, then we actually have the permutation 1, 2, 2, 1, and 1, 1. We don't include 2, 2 because it's repeated by 1, 1. So we're gonna look at that in a few slides though. Cool, so the next point is, if the slides move, is can we scale above sort 5? And here actually is one of the limitations of the algorithms that we're going to talk a little bit more. Because exactly as the question asked, how do we measure correctness? We need to check every possible input permutations, and that can grow very expensive. So there are three key components that we were able to scale to sort 8. So the first one, what we call the assembly graph net, which is a different way of modeling the programs in a more efficient way for learning. The second one is the 0-1 principle, which we apply to assembly sorting networks, which we're going to talk in a few slides. And finally, we use μ0 instead of AlphaZero. So for those of you who are familiar with AlphaZero and μ0, when it does Monte Carlo tree search, it searches on the latent space. So it's much cheaper to do this operation, which is usually quite expensive. So looking at the graph nets, we decide to model programs as a graph, where each node here is going to be either a memory or registers, and edges are instructions which correspond to the data flow. So if you have, for instance, move from memory 1 to register 1, we are going to have a connections between the memory 1 to the register 1 here, which is labeled as A. So modeling programs with a graph adds a prior information to the learning, and it's what allows us to learn better when the algorithm size increases much further. Then to answer the second question is how can we check for correctness in an efficient way? We relied on this 0-1 principle. So what is the 0-1 principle? Well, the 0-1 principle is a theorem for sorting networks. So this principle says if a sorting network sorts all binary sequences in 0 and 1, then this sorting network sorts all sequences of arbitrary numbers correctly. And why do we like this theorem? We like it because what you see here is how it grows. Like for sort 8, you only have 255 inputs of 0 and 1. While for the Bell order, which is what we normally do, you have 500,000. Massive difference. But the question is, does the 0-1 principle apply to assembly sorting networks? And the reality is not exactly, but what we were able to do is come up with assembly sorting networks first, and then prove a condition where this applies. So going very quickly, this is an extension of the definition of sorting networks applied to assembly, where edges represent moving instructions. So here you're moving from the first memory location to the first registers. This is just a compare operation, and then you have conditional moves. So we came up with this extension to the theorem that says, okay, if every conditional move operator is only applied to values that fall within the range of a previous comparison, then the 0-1 principle applies also to the assembly sorting networks. And this is a great news for us, because that condition is not too restrictive. So we just need to make sure that we respect it, and then we can just check the permutations of 0 and 1s, making it the whole procedure much faster. So that worked, and we did try first on sort 6. And we are very happy that we were able to discover 57 instructions, and that is 3 instructions shorter than the human benchmark. Then we applied to sort 7, and again we saved 2 instructions. And finally to sort 8, and then we discovered 1 instruction shorter than the human benchmark. We discovered 91 instruction programs. Cool. So we can extend over sort 5, we can go up to sort 8. Now the question is, can AlphaDev generalize to domain other than sorting? And if there is an algorithm that is maybe as notorious as sorting, well, there has to be hashing. So probably everyone here knows hashing is an algorithm that has been around for more than 70 years. Initially was invented to bucketize information to speed up search, and now it's prevalent everywhere. It's used for information retrieval, information storage. It's a key component of data structure like hash maps. And we started with the goal, actually, the goal of hash maps, especially around upscale flat hash map, which is a very common data structure in C++ programs. Our goal there was if we can optimize the hashing function of the data structure, because it's so prevalent in every program, then we're going to affect all programs out there. So how do we adapt AlphaDev to work on hashing? It's actually very simple, because the definition of AlphaDev, the structure of AlphaDev that Dan described, is quite general. The main change is changing the correctness definition. Now we don't have the same correctness as sorting, where we need to check every input permutation. We define correctness based on the number of collisions. So we start from an arbitrary input distribution. AlphaDev comes up with a program. We run the program over the input, and then we measure how many of these outputs are the same, right? How many collisions do we see? And again, we want to minimize the number of collisions and minimize the latency as well. So the fastest program that minimizes the number of collisions. And what's interesting is that the approach for latency, nothing changes there, right? The same latency benchmarking server that Dan talked about is exactly the same. Another small difference is the set of instructions that we use. When we optimize for sorting, we weren't using rotations and bit shift that are not so useful for sorting, but they're quite important for hashing, of course. So here some of the results that we target. On the left, what you're seeing is the previous hashing function upscale flat hash map. And the part highlighted is for bytes between 8 to 16. And you can see that this mix function is called twice. This mix function does a multiplication. And what was interesting is what AlphaDev discovered, which you can see maybe a bit better on this slide. So it replaces two multiplications with a rotation and multiplication. And especially the rotation is quite interesting because it rotates the low bytes by 53. And we found this 53 constant was very interesting because we didn't select it, right? It was the agent that came up with. And we noticed that they tend to come up with 53 and 11, which are kind of complement of each other of 64. And it seems that this constant is very well to mix both the low bytes and the high bytes. And it's one of those discoveries that it takes quite a bit of time to understand why does it work so well theoretically, but we are really pleased that the agent is able to find. And it's one of those optimizations that, of course, are very hard for us humans to come up without, it's much easier for a computer to discover. Cool, so how does this part of the algorithm fits in the whole hashing function? We modified the red part where we have to mix with the new algorithm that we modified for bytes from 8 to 16. So similar to sorting, we really wanted to get this deployed, right? We didn't want to just have this discovery and measure the latency and just publish that. We really cared about these algorithms being deployed out there in open source libraries. And of course, you can imagine it's not that easy, right? There are so many programs and libraries that depend on upscale. And because we cannot check every input distribution, what we were doing is that we were trying to measure, like we were starting from an input distribution and measure how fast it is. We are lucky that there are tools like Smasher that offers a suite of benchmarking tools and really test these hashing functions to see how they perform. And also the upscale library as well has some benchmarking utilities. And there was quite a lot of back and forth here to find the right input distribution to start AlphaDev with in order to find the right hashing function. And depending on the inputs that you start, of course, AlphaDev would come up with a different one that would optimize specifically for the input. We are happy that after a few back and forth, we are able to discover a really good and robust hashing function, and then has been deployed to upscale, and has been accepted. And what we observe is about 30% improvement over the previous function, which is huge. We estimated conservatively that this function is called about trillions of times, very similar to sorting. And also, as far as we are aware, it's the first time that RL has been used to optimize this library. And the other point that I'm really happy is that it shows that AlphaDev can go beyond sorting, and this approach is quite general, the approach of optimizing end-to-end with latency. Cool, so now let's take a step back, right? And let's think a bit, what type of algorithms suit AlphaDev when it's not a good choice. We talked a bit about exhaustive search, and in fact, this is the first kind of requirement, right? If exhaustive search verification is possible, then this is a good fit for the algorithm, right? Sort tree, you can check every input. You're confident that the function that AlphaDev discovers is correct. Then this suddenly is not always possible. But there is another condition that, that we have. If exhaustive verification is not possible, then at least we want a definition of quality, right? And that's the case of hashing. In hashing, we are not checking every possible string, but what we want to see is that how does this hashing function performs on average over like a production input. And so if either one of these two conditions fits, then we can use AlphaDev to optimize the algorithm. And we are lucky that there are quite a lot of algorithms that fit in this category, right? Like any type of hashing, serialization, deserialization, type of lossless algorithms, and so on. Cool. So how does AlphaDev compare to other state-of-the-art approaches or the literature? Of course, the literature for program optimization and program synthesis is quite big, and in the paper we do a bit of a in-depth analysis compared to other approaches. There are approaches at the assembly level. RL has been used before as well, it's not the first time, and deep learning. I think the main difference is that we optimize end-to-end for latency. And that makes a massive difference because other approaches tend to optimize either for program length, which doesn't work as well when you have branching, or maybe they assign a cost to each instruction. And that doesn't work with modern architectures. In modern architecture, sometimes you have parallelism between instructions. So few instructions can be executed at the same time. So if you assign like a fixed cost to each assembly instructions, that is not gonna work as well. And cool, but what are current limitations? Quite a few actually. So our current setup right now doesn't support loops. There is no particular reasons, like we support forward branching. A loop in assembly, of course, is just a jump backwards. It's just a bit of engineering reasons. Once you have loops, of course, you have the halting problem. Like even for measuring latency, you need to make sure to unbound things and making sure, okay, when does it terminate? You're gonna create a lot of programs that never ends. Also, I think we would need to adjust a little bit of the modeling to make sure that these loops are well understood by the program. But I think the graph-nets and transformers should do that in principle. The second point is that I really would like to see AlphaDev to work with SIMD. So SIMD is vectorization, and it's an area which is very hard to optimize for humans, but I think there is a lot of headroom. If we can have something like AlphaDev that comes up with very efficient vectorized algorithms, I think it would be really, really cool. And third is that right now the space that we operate at is the assembly level, which Dan gave a few reasons why we will operate at the space, but it would be really nice to maybe work at a higher level, especially when we care about the algorithms being deployed, or every time we had to reverse engineer from assembly to C++. So maybe generating directly in C++ would be ideal here. And yes, future, where are we going from here? Well, when we did the comparison with stochastic search, we noticed a few setups where stochastic search is a bit better than AlphaDev, can be a little bit more efficient, especially searching on a local space. So maybe a combination of the two would be quite nice, where AlphaDev with its planning capabilities of RL can come up with novel programs, and then we apply some stochastic search to search locally within the space in order to find the most optimal solution in that particular space. Second, of course, we all see like how much language models became powerful, especially with code. It would be very interesting to combine the two, right? So you have a language models as a strong prior that has seen all the code out there, and then we add some planning capabilities of AlphaDev to actually like both target higher level languages like C++, for instance, but also have been able to come up with novel solution. And finally, my dream would really be if we can tackle both the hardware and software stack at the same time. And I really hope that one day we'll get there. So in conclusion, AlphaDev discovered faster hashing algorithm and sorting from scratch, and we were able to deploy both in open source libraries, so they're available to every developers, libraries, and programs out there for C++. And second, like we observed that there are a lot of opportunities in this space for RL. And I'm really happy because often like most of the victories of RL are in the games, right? And this is another example when RL is used for a real world use case successfully. So we left the contact details for any, feel free to contact us, but we are more than happy to answer any question you may have.
Okay, yeah, I think, yeah, there is no audience microphones here. So feel free to raise your hands. We will hand you a mic. If you are online, write your question on the chat and we will read it aloud. So.
Hi, thank you for a really amazing talk. Very great work. I just wanted to ask, so if I understand correctly, the during training, the distribution of input sequences for sorting is random. I guess in kind of real world sorting applications, there are some people looking at, okay, well, what if the distribution at test time is not quite random to your sorting sequence, right? So maybe more often than not, your algorithm sees an input sequence which is sorted in the reverse of how you actually want to sort it. So do you think this is an interesting line of future work for this? It seems quite easy, quite naturally to fit with your method, right? Because you just need to change the training distribution. Or do you think maybe this is actually not that useful when you are only looking at like sort 5 or something like this and actually randomizing it?
Yeah, I mean, I think it's probably one of the most impactful things to potentially work on. You know, we found that AlphaDev was very good at fitting to a distribution. It would design a function for a particular distribution. We had sort of the constraint with the functions we chose that it needed to be sort of general and so the distribution needed to be random. But I think this is a place where if you're able to exploit the distribution, there's a lot of gains to be had there.
Maybe one thing to be mindful of is that these libraries are public. So you can optimize for a particular input distribution as long as you need to make sure that it applies to everyone. Especially for sorting, they have libc++ have a set of benchmarks that checks all the use case, right? So completely sorted, completely unsorted, random, and so on. But then, yes, if you have a particular input distribution that you really care, you can target that. And the algorithm does that very well.
Thank you very much for the presentation to start with. And I wanted to ask, like, regarding when you explained that you use the transformer, like, to get the state representation of like the assembly codes. My question is, up to what extent there could be like a bias and such representation by the fact that these codes have been created from our previous understanding of how these algorithms have to be optimized or something like that. So maybe like once you have like AlphaDev working, it's possible to feed back new representations and new assembly codes that can expand this connection between like the code and the function of the code or something like that.
So to paraphrase your question, are you saying that you can, as you're learning, as you're learning and you learn useful representations with your transformer, you can somehow reuse those representations in order to sort of bootstrap the learning capabilities of the agent on other problems. So like you could go sort of maybe from, if you learn sort of a representation that's relevant for sorting 3 elements, and then there's a similar structure for sorting 4 or 5 elements, you could reuse that somehow. And that's possible, that might be possible. I mean, it's something we spoke about. I think we were talking a bit about curriculum learning, and I think this is something that could be very relevant here, where you know, if you're able, I mean, it's under the assumption that the structure you learn for sort 3 is relevant to sort 4 and onwards. But I think that we saw that there were a lot of similarities. So that might be one way to do it.
Because maybe like at some level, that's some like new solutions were like kind of surpassing like the human benchmarks. Maybe these kind of representations can be fed back in order to create new representations that were not contemplated. And yeah, I think it could be like an optimizing like loop and so on.
Yeah,
thank you very much.
Point. Sure.
Hi, thanks for the talk. I was wondering how well AlphaDev like explores the space, or like rephrasing my question is like, how confident are you that like sort 3 is now the best there is and we don't find anything better?
Excellent question. So we tested this out, and so after we discovered the 17 length program, we said, well, can we do this with brute force? And we spent quite a while setting up enough processes to run this brute force. And with some assumptions, we eventually managed to do it. And I think it took about 3 days to discover sort 3, 17 length program. So it was actually possible to do it with brute force. But beyond that, it was just completely infeasible. We really took together all the engineering skills we could muster to sort of brute force sort 3, and then we were like, okay, there's not much more we can do beyond this. So yeah, so for sort 3 you could do this, but beyond that it's infeasible.
For instance, for sort 4 we were not able to save any instruction, and I spent a lot of time trying really hard. So if anyone comes up with a 27 sort 4 program, I'll be very annoyed. And of course I'll be really happy. But yes, we will never be able, we don't know what's the headroom there, sadly.
So no further questions. Okay. I think then we can finish here, and with the food and drinks, you can still discuss with the speakers. So thank you very much both for coming.
Thank you so much for having us.
Thank you, everyone, and hope to see you next year.
Yeah.